Okay, now we can dig in the coding itself, the implementation itself of those IDs. So we are going to return here whatever is returned by our recursive function. Our recursive function, I'm going to call it search for ease, okay? I'm not going to put it in the header because I do not want the test.c or any other application to be able to call it directly. I'm going to offer an interface to every other programmer, an API, application programmer interface, which is every time you want to search in an int array, call this function. Now, whether internally I need another function to be able to do the job is my problem. My problem meaning the implementer of this function problem. Nobody else should know about that. So I'm going to here relay this call to int array search to a call to a hidden, if you will, search function, which will not be able to be called by test.c because it's not in the header. And this function is going to use as parameter the value, the array, the start index, which is going to be 0 the first time we call it, and the stop index, which is going to be size -1. These are inclusive. Okay. Now I can work on implementing this function. Int search, int val. Same thing, same signature so far, okay, for the value and the array. Instead of having a size, I have delimiters, so int start, int stop. These are the boundaries of the subarray of data in which I need to make my search. So let's get started. What do? Well, I'll try to get rid of all the stop case, the case that I can reply to immediately without doing further work. That's a good strategy for every recursive design. So in this case, what does that mean? Well, that means that, okay, if start equal stop, well, in that case, return what? I know that I have exhausted my array. I'm left with one location in the array which I didn't test it. So I'm going to go ahead and test it now, and I'm simply going to return the result of that test. So if data start equal value, I could use start or stop since they're equal, that doesn't matter. If it is equal to value, then I found it. Otherwise, I didn't find it. So I got rid of the obvious stop condition that we described before in the design video. Now, what else can I try to do here? Error condition. Well, I'll let you decide whether it can happen or not. But what happens if starts becomes suddenly bigger than stop, something like that? Well, I would potentially have to handle it. So I'm not going to handle it so that you keep working on whether this is a possible case or not. And if this is a possible case, I'll let you implement it. If it's not a possible case, then we don't implement it. What else? Well, what happens if start is actually lesser strict than stop? So we are still searching. We need to determine what is the middle index of the subarray. Okay, what is the middle index of the subarray? Well, we are going to play with indexes here, so it's really easy to make an error, so let's take the time to think about it. My end index, named stop, minus my start index is going to tell me how many array elements are between the two. So let me get back to my scratch paper here. Let's see if I didn't lose my mouse, it would be easier. Let's take a new page. And second example, I am in the middle of an array search. Okay, this is here my start index. Let's say this is index 3. So there are more elements here. 4, 5, 6. Stop is index 6. Okay, so what are we trying to do here? If I do stop minus start, I'm talking about 6 minus 3. This is telling me that there are 3 elements in between. Okay, well, this is one element here in the subarray. I mean, an element here, an element here, an element here. 3, 4, 5, 6. Yeah, it's not really working great. So it's not telling me exactly how many elements total there is. That would be 3 plus 1. Okay, so once again, if I want to know the size of the subarray I'm considering right now, I take the end index, 6. I subtract the start index, 3. I add 1 to this number, and this tells me how many locations are in this sub-array, right here, 4. Okay, so alright, that helps make a little diagram here. Back to the code. So I'm trying to determine which one is the middle element. Okay, so I have this number of elements. I'm going to divide by 2. 4 divided by 2 integer division, going to lead to 2, and I'm going to add start to this. Start is 3. This is going to give me 5. Let's see, index 3, 4, 5. This is going to apparently round up. But this is a good start. I divide by 2 the number of elements. I had the start index, which can be anything, not only 0, okay? And I'm going to end up with one of the two middle elements in that um, even number of location in this subarray. Okay, so we have a sketch here for our function. Let's work on it. Let's try to put that into code. Middle is going to be equal to stop minus start, and then I'm going to add 1. This is what I did in my little simulation, okay? Stop minus start plus 1, number of elements in that subarray, divided by 2, integer division, so this is going to round. And then I'm going to add the index start. And this should tell me like what is the index of the middle element of this subarray. Assuming that this is correct, and part of our job will be to make sure that this is working, what do we do next? Well, we are going to test the middle element. So if data index middle is actually equal to val, well, if it's equal, we just found what we were looking for. So let's return 1. Else, if it's not equal, since my if statement is going to return something if it's true, I don't have to use else. I will be here on line 60 only if the condition above was not true. So now I'm testing if data index middle is less strict than val. Well, what's happening is that val is too big for this value, for this middle value, so it's going to be on the second half of our array. Return the result of searching for val inside the array data between indexes, while this time middle to stop. Else, if it's not equal, if it's not lesser strict, it's bound to be greater strict. So that means that this value is actually going to be in the first half of my array. So that means between start and middle index. Okay, well, it looks like we have like some rounded up code. Before we compile, let's take the time to think about it to verify the logic. So the first thing we need to verify is the logic of this formula. What did we try to make sure that this was correct? We tried on one example here between index 3 and 6. Okay, so this is an even number of element. Let's try with an odd number of element. So I have an array here. Let's say that this is index 3. So there are more elements here. This is index 3. Let me try with index 5 instead of 6. So this is start, this is stop. I apply the same formula. Okay, stop index minus start index plus 1 divided by 2 should give me this should give me the number of elements in the array divided by 2 plus the start index. In this case, this is 2. 2 plus 1, 3. 3 divided by 2 integer division is going to give me 1 plus 3. This is going to give me 4. So this would be my middle index. Okay, these are the two cases that could occur. Okay, we have an even number of elements in the subarray or an odd number of elements. Well, I've been like simulating what would happen with this formula with both. I'm pretty confident right now that this code therefore is correct. It seems to lead to the appropriate answer in both type of situation. Now, what about this logic here? If the data middle element is equal to val, return 1. No quarrel with that. If the data middle element is actually lesser than val, well, we are ordering this array in ascending order. Okay, so if val is greater than the middle element, then it's going to be found in the last part of the array, the second half of the current subarray. This is what we did here. Start at middle, stop. Therefore, this logic is correct as well. So we have some code. We did reasonable efforts to design it and to verify the design on paper. Now we need to make sure that it compiles and then test it. So let's get rid of the compilation step. Couple of problems with the compilation step, as you can see. Let's start with hold.c line 50, implicit declaration of function search. Well, that would be easy enough to fix. Here's what's happening. I'm calling the search function before I even defined it. Well, I'm not going to add search in a header file, but I can add its prototype here. Int val const int data, and I see that I've made a typo on line 53 with the keyword const. I'm going to address that. Int stop. I have the prototype, therefore I can call it here, and then I can define my function. I could have just as well cut and pasted everything that is between line 55 and 65 above line 50, so that the function would be defined before I actually try to test it. So I corrected normally 2 bugs here. Let's go back and see how this reflects on the compilation log. That was it. These were the only thing that were posing problem. No need to even run it because I didn't start testing it. Instead, let's go to the test.c file and let's try to figure out a way to test this little algorithm. So we are talking about being able to search for a value in a sorted array. So the first thing we're going to do is to try to call our function on a non-sorted array to see if the isSorted function is called properly from within the search function, which we didn't do. So this is how we are going to catch this kind of forgetfulness. So here, from the test perspective, that means printf testing int array search function. Okay, _n, and now let's put our test to work here. I need an array first. Okay, let me see. Well, we're not asking for the user to provide us with an array. We're going to make it interactive. Int array scan, and I'm going to use my array. Why not? So I'm going to rescan my array. Printf little invite here. Tabulation is enter an over array. _n. Scan this array from the user. And then we are going to try to search first. Printf trying to search in unsorted array. Enter another unsorted array would be more appropriate. And here I'm going to call int array search value. I'm going to use a variable I'm going to define in a second. Search inside of my array of size 9. If this returns true, I'm going to printf found. Else, I'm going to printf not found. Okay, so the only thing we have to do is to take care of this value. So printf \t enter value to look for. I am going to declare an int, let's call it v, just to make sure that we don't call it the same thing as the parameter. Int v, and I'm going to scanf a %d, which is actually going to be stored in the variable v, so that I can then try to search for my variable in the array. I save. Let's give a spin to this code here. GCC first. Okay, a.out. So this is still the old testing code. Okay, I'm going to give it the same value I always do. Okay, testing int array search function. Enter another unsorted array, size 9. Let's keep the same. 6. Actually, yes, I said let's keep the same, but I apparently decided to take something different, so we'll work with that for this time. So I entered a different array. I'm now asking for a value to look for. Let's say I want to look for value 3, a value which is there. Segmentation fault. So my array is not sorted. I try to look for a value which is there, and then I plan, of course, on looking for a value that would not be there. But I'm not even allowed to go that far. This is segmentation faulting. Well, this is just telling me pretty much that I am iterating the wrong way in an array. I'm getting out of the boundaries of an array. So this can be really complicated to look for. However, in our case, this is going to be very simple because this is just a reminder that when I try to search my array, I do not verify that my array is actually sorted. So if int array is sorted of data size, if this is true, then I can start my search. Else, I should return -1, just to mean I cannot search this array. So that means that in test.c, I should look for this return value as well. So let's do it. If, let's do an int result equal calling int array search, blah, blah, blah. So we have the result, and then we can check this result variable as many times we want. If result is equal to 1, well, if result is true, let's simplify here, then printf found. If result is actually equal to -1, then printf error array not in ascending order. And I'm going to move this up because I just realized that yes, if result is -1, I want to say error array not in ascending order, and I don't want to even try to interpret whether result is true or false, because if I was trying to test after that if result, that would be true. -1 is true, right? So instead I'm going to put it in the else so that this doesn't happen. So I have here printf error array not in ascending order if result is not -1, and if result is true, then printf found. Else printf not found. Okay, that sounds reasonable. Let's save this file. Go back to Conqueror, and we're going to just test this. So recompile a.out. I'm going to comment those tests very soon so that we don't have to go through them. But right now, I'm going to re-enter my array, all the values. I want to look for 3. Trying to search in unsorted array. Error, the array not in ascending order. Okay, well, that's not working. That's what we expected. If we if we run it again, and I'm going to skip over that. Blah, blah, blah. Okay, now, this is the important part. 2, 3, 6, 4, 5. If I try to look for, let's say, 10, error array not in ascending order. So we are not yet there. So let's go back and let's try to debug this, okay? We are going to start by the beginning, test.c. First thing I'm going to do, I'm going to simplify my task because I'm going to have to test a couple of things, obviously. My code is not yet working, so I'm going to comment my old test and only let activity the current test, okay? Since I have a bug in this one. Testing int array search function. Let's review a little how I do the testing here to make sure I'm not doing something stupid. I'm testing the int array search function. I'm asking for an unsorted array. I get an array from the user, which I store in variable myArray. Enter the value to look for. I get the value to look for. Trying to search in unsorted array. And I get here error, array not in ascending order. Well, yeah, this is a non-sorted array, so that makes sense. Can I even ever reach here found or not found? Well, not with my unsorted array. So I should expect that the first time I try to look for value v in my array, I'm going to get that message systematically. Okay, that makes more sense. Now let's go back then to try to test other things. What if I sort my array? So this is my array size 9. What if I sort it and then I try to search in the sorted version of the array? Trying to search in sorted array. Well, This is going to work the same way, except I don't have to redeclare here int result. And I'm going to check if result is -1, then there would be a problem. Okay, array is not in ascending order. Well, okay, I just try to sort it here. So normally the second time I try, I should have no problem with the error case, and I should have a response which is found or not found, depending on what value I specified. Okay, so let's save. Let's once again compile. Let's run. So we skipped all of the beginning stuff. Okay, let me just enter my values here. Value to look for, 3. So this is a value that belongs to this array. Searching in unsorted array, error. Searching in sorted array, found. Okay, that's good. Let's try again. 9, 8, 7, 1, 2, 3, 6, 5, 4. Value to look for, 10. Error the first time, not found the second time. So we have good indication here that this is working. This is pretty much it for this exercise. Okay, the main thing that would be worth doing at this point is try to rework a little the test code, actually this code here, to try to reorganize it, because as you can see now, we would like to be able to easily comment out, code tests that we are already satisfied with. And in the long run, I mean, we are still doing all of our testing by hand, so this is fine to a certain point, but now we would like to start considering how we're going to be able to transform this test.c, which is really drafty right now, into something that we can use for automated testing. Okay, something that is going to display a message on the screen only if a test is not actually is failing. Okay, so like we did with the previous exercise theory.